welcome back. In this lecture, we are going to discuss hardware implementation of mixed signal current mode control with some experimental result. So, here we will show we have discussed in the previous lectures, I mean 2 or 3 lectures, where we have discussed mixed signal current mode control implementation and programming using Verilog HDL. So, now we will show implementation details, whatever we have used in our experimental setup and some experimental result with transient performance. So, mixed signal peak current mode control architecture we have discussed multiple times, and for this converter prototype that we are going to demonstrate, we have considered the inductor to be 1.8 microhenry, capacitor to be 200 microfarad, and we have considered nominal input voltage of 3.3 volt, and the output voltage is varied between 1 to 1.1 because we have shown also reference transient. So, the nominal output voltage is 1 volt, and the switching frequency of considered 200 kilohertz, and we have considered one continuous load resistance RC and a switch resistance is 0.33 ohm, because if we consider the buck converter output size stage, so we have considered one continuous resistance, another switch resistance. This is our switch resistance where we have considered Q load, and we make it either load 0 or 1. 0 means it will operate at a lower load condition, and 1 means it will operate at a higher load condition because the effective resistance going down. So, in the control architecture, apart from the power stage, we have shown this diagram, that means the actual implementation in the previous 2 lectures, where we have considered that we have a feedback gain, voltage feedback gain, which is decided by the resistive divider, and this gains is nothing but 0.27. Okay. And then we have considered a 10 bit ADC, that is why the ADC resolution is 10 bit. We have considered a DAC, which is a 12 bit DAC, that we have discussed, the 12 bit DAC, and we are using controller clock, which is the controller clock to be 100 megahertz, and the current sense gain, because we have used a current sense resistance followed by a current sense amplifier. So, it is coming to be 0.01 volt per ampere, because it is converting current into a sense voltage, and that is compared directly with the output of the DAC. And the DAC Vp can vary between -1 volt to, I would say -1 to, so it should be in the closed bracket, that is the lower limit, to 1 volt. Okay. So, that is the detail, and we have considered this PI controller where proportional gain is 4.75 and the integral gain is 0.4. Okay. And we have discussed the current reference, date time, all this detail in the previous lecture. So, the digital controller PI controller gain that we have discussed in the actual code, we have taken 4.6 and 1.9, sorry, it is in the 4.6 Q format and Q 1.9, and the proportional gain we have discussed, it is how much it is, 4.75 and 0.4, 4.75, and this appears to be 0.4. So, these are the gain. Now, we are showing load step up transient. So, we have applied, that means we have considered, if the output capacitor side, we have a continuous load which is 13.5 ohm, and then we have RSW, and this RSW is 0.33 ohm, and we are considering one external load, that is MOSFET to turn on and off. So, this is the condition at this is 1 volt and this is under lower load condition, that means here your load resistance. So, effective load resistance either can be a simple RC under light load condition, and under high load condition it is a parallel combination of RC and RSW. So, you are making a load transient, and if you look at the load transient response, the undershoot which is here, this undershoot is coming to be roughly around 175 millivolt to like roughly 170 to 180 millivolt, and we are getting a load settling time of around 80 microsecond. And if you go to load step up transient, step down, so we are getting again the delta V, the overshoot is roughly around 170 millivolt, and the settling time is coming to be here, so like 60 microsecond. But again we will discuss about design aspect by which we can shape the transient response, and this seems to be quite good, quite fast, because you see the current is ramping down fast. So, this overshoot something that you have to accept, because the load has gone down. So, you will have a excess capacitor charge and that has to be discharged by the inductor. So, reference transient also you have considered, where we have set the load resistance to be at RC, that is to be 13.5 ohm, that is the load resistance, fixed load resistance. So, in this case it is 1 volt reference and here it is 1.1 volt. So, we will have some additional overshoot in the output voltage. So, this additional overshoot which is coming delta V, that is equal to, so on top of this 1.1, so we are getting around 50 millivolt overshoot. For 100 millivolt is the load reference step transient. Similarly, we are getting undershoot here also, so which is delta V, this is also around 50 millivolt. And if we go to the, this is the more detailed response, the settling time is coming to be this much, that means around 50 to 60 microsecond, we can take up to this point. So, if we consider up to this point, so this point 50 microsecond, and overshoot is around 50 millivolt, and if you consider the undershoot, it is also around 50 millivolt. But in this case, this is coming to be roughly around 40 microsecond. Okay. So, that means we can actually load transient and reference transient response we have discussed in current mode control, and in the subsequent lecture we will discuss about the design aspect. So, in summary, we have discussed digital current mode control implementation using mixed signal domain, where the current inductor current is analog, implemented analog loop and with analog current loop and digital voltage loop. And we have also discussed mixed signal peak current mode control experimental result with some transient performance. So, in the next lecture we are now going to consider what will happen in discontinuous conduction mode, and we will be discussing about pulse keeping modulation. That is it for today. Thank you very much.